I didn't say you weren't.
I was like, I'm sorry.
I was just saying.
All right.
So now we're like, about recursive integrals.
Throwing it down.
So in chapter 14 is all about how we integrate multivariable functions. And for this, in this chapter, we're looking at definite integrals only. And we'll do some indefinite integrals in chapter 15, and we saw kind of an example of that on our test as the bonus question. And the reason we're doing definite integrals only is because with a multivariable function, the constant of integration, if we integrate with respect to one variable, can be a function of the other variable. Because x is constant with respect to y and y is constant with respect to x. So our constants of integration can be functions of a different variable. So I want to start with an example. So if we have the integral from e to the y to y of y natural log x over x dx. And we're going to say y greater than 0. So we don't have any problems here. We'll give an interpretation to what this integral is telling us in just a little bit. But for now, we just want to evaluate this. So in this case, our variable is x, and y is constant. So these limits of integration, e to the y and y, that's going to be constant with respect to x. So we have constant limits of integration with respect to the variable that we're integrating with. All right, so this integral, if we evaluate this integral?
U sub.
It's just a u sub. U is natural log x, du is 1 over x. So dx. So we end up with, and y is a constant, so we end up with y out front, and we have our u is natural log x, we have a dx, so we have a natural log x squared over 2, and we're evaluating that from e to the y to y. And I'm going to write in here, because what we're doing, x equals and x equals. So x is our variable, so x goes from e to the y to y. So when we evaluate this, we get y over 2 ln y squared minus ln of e to the y squared. When we substitute in our limits of integration, and at the end we get y over 2 ln y squared minus y squared. So when we do do this integral with respect to x, the function that we end up with is a function of y, which with respect to x is a constant. Now we could, at this point, integrate this with respect to y.
But why?
And that's what we're going to do soon. All right, so let's look at another example. So the integral from 0 to x to the third of y e to the minus y over x dy. This time y is variable, and x is constant. So this one, so when we have something like this where x is constant, but it's in the function, it gets it can be a little difficult to make your brain turn the switch to think of x as a constant. So what is it? How are we going to integrate this? This is going to be integration by parts. This is like essentially we have y e to the y dy. So we're going to do integration by parts. And I'm going to set it up kind of the traditional way. Integration by parts. I'm going to say u is y, du is dy, dv is e to the minus y over x. And remember, we're doing this in terms of y. So v, when we integrate e to the minus y over x with respect to y, what do we get? Negative 1 over x, e to the minus y over x. So we think of x as a constant. Just like as if this were negative y over 2, e to the negative y over 2. We do it the same way. So we have minus, so it's u dv, or sorry, u times v. So we have minus minus x e to the minus y over x. Yeah? What's that?
Jesus.
From dv to v, you derive.
That should be x. Should be negative x e to the negative y over x.
Oh. Thank you. All right. I wrote it correctly here, right?
Yeah.
Yeah. All right. So there we go. Minus, and I'm leaving off my limits here. We'll put in the limits at the end. X e to the minus y over x dy. And x is just a constant. So this equals minus xy e to the minus y over x plus, and we're integrating x e to the minus y over x, so we get a minus x squared e to the minus y over x. And we evaluate this on our limits. So we evaluate from 0 to x to the third. And here this is y equals 0 to y equals x to the third. So we're substituting for y. And when we have an integral and we're evaluating an integral that has an e in it, remember e to the 0 has a value. It's as easy to say, oh, we don't have to worry about that. So I'm going to write this out. This equals minus x to the fourth e to the minus x squared minus x squared e to the minus x squared. So this is at my upper limit of integration, minus 0, because y equals 0, minus x squared. E to the 0 is 1. And finally, that I can write that as x squared, 1 minus e to the minus x squared e to the minus x squared. And notice now we ended up with a function of x, which we then could integrate with respect to x. And if we integrated this with respect to x, we'd have some nice additional integration by parts. So the nice thing about these one nice thing about these kinds of integrals is you end up doing multiple techniques in a single problem. Mm-hmm. All right, so this idea leads us to the concept of an iterated integral. So we can integrate we can integrate once with respect to one variable, and then again with respect to another variable.
It's like the opposite of partial integral. It's a mixed integral partial.
So we can iterate this process. So I want to go through a couple of examples here. So we can integrate from 0 to pi, the integral from 0 to sine x, 1 plus cosine x dy dx. So that would be an iterated integral. We do these kinds of integrals.
Inside y is going with which integral?
Inside Dylan.
We do this inside out.
Just like that movie.
So we're doing this integral first. So what we're thinking of is the integral from 0 to pi of this integral dx. So we do the inside integral first, and then we do the outside integral. So here x is the variable, and y is the constant. So we get the integral from 0 to pi. When we integrate this with respect to y, what do we get? We get y plus y cosine x, right? Because cosine x is constant with respect to y, and we're evaluating that on 0 to sine x, and then we're integrating what we get out of that with respect to x.
Oh dear.
So when we evaluate that inner integral, we get sine x. This is y equals 0 to y equals sine x plus sine x cosine x dx. And this is not a bad integral. And we're evaluating that from 0 to pi. So we get minus cosine x sine squared x over 2. And we're evaluating that on 0 to pi. And again, with trig functions, be careful, because some trig functions evaluate to a value at 0. When we evaluate this, we get 2.
These integral debates, you have to give us like a whole sheet of paper.
Right.
Yeah, you're not gonna.
What if you had a chain of like a bunch of
And we can do it.
Going up the alphabet.
yeah, A through Z.
It's gonna make it so hard.
So when we evaluate our inner integral, we get a function, and when we evaluate our outer integral, we get a constant. The inside limits of integration can be variable with respect to the outer variable. The outer limits of integration have to be constant with respect to both. So when we evaluate our iterated integral, we get a number, not a function.
Now, what are we doing in the rest of the
We're going to apply these things,
Oh dear.
and we're also going to learn what these are iterated integrals. We're going to learn about double integrals and triple integrals and various other kinds of things.
If I hope, then like there might be a chance.
All right. The union of the two intervals of integration is the region of integration. And we usually call it called R. R for region of integration. In the last example, R is 0 less than or equal to y less than or equal to sine x, union 0 less than or equal to x less than or equal to pi. And in the plane, y goes from 0 to sine x. Well, there is sine x from 0 to pi. So this would be the region of integration. So a region of integration is a region in the xy plane. And a big part of what we're going to do in chapter 14 is work on the skill of going back and forth between regions of integration and limits of integration, and regions of integration. When we start talking about triple integrals, we're going to have a region of integration bounded by a surface. Or a region of integration might be the intersection of two surfaces projected down into the xy plane. All right, are we good so far? So let's give an interpretation, one interpretation to an iterated integral that's going to let us work with these limits of integration and our regions of integration. So we're going to talk about the area of a plane region. So this gives us a geometric interpretation of these iterated integrals. So here's a region in the xy plane, and we want to find the area. I'm going to call this G1 of x and G2 of x. And we want to find the area of this region between x equals a and x equals b. Now, we have a technique for doing this already. But what we want to do is apply what we're thinking about with iterated integrals to come up with an interpretation of that of the iterated integral. So what we're going to do is divide this region into little rectangles. And we're going to say the width of the rectangle is dx. So we already have a technique for this, so we're going to apply iterated integrals to that. Yes?
Are the top and bottom supposed to be like the same curve?
No.
Okay.
They're two different functions. All right. The area of one rectangle. We're going to write the area of one rectangle as an integral. The area of that one rectangle is an integral. So we're going to divide this little rectangle into little pieces. dy. So how would we represent the area of that one rectangle as an integral? The integral isn't our area just going to be the integral of dy from g1 of x to g2 of x? Yeah. So if we evaluate this, this gives us y from g1 of x to g2 of x So we get g2 of x minus g1 of x, right? We've done this before. But the area of one rectangle is the integral of dy from g1 of x to g2 of x. If we sum the areas of those rectangles as we go from x to a, from a to b, so the sum of the areas of all the rectangles as x goes from a to b is, well, we're going to integrate now with respect to x. We're going to integrate x equals a, x equals b, the area of each individual rectangle dy, and we're going to evaluate that outer integral with respect to x. So the sum of the areas of those rectangles is an iterated integral. So we can represent the area of a plane region as an iterated integral. Now we know that to find the area of this thing we do top minus bottom. But what we're going to do now is apply this thinking to do other things with iterated integrals. So we're going to, for example, maybe we have a surface over that area. And we want to find the volume of the surface that's bounded by this area in the xy plane. That's one application that we can use. And this is not the only interpretation that we're going to give to iterated integrals. This just gives us a geometric interpretation. Now, we call this kind of region where we're bounded at the top and the bottom by functions of x. We call that region vertically simple. And we set our representative rectangles vertically. So that the top and the bottom of the rectangles are bounded by functions of x. We can set up our region of integration where the left and the right of our region are bounded by functions of y. So let's draw a picture of that. So we could have something like this. And I'm going to call this h1 of y and h2 of y. And we're going to go from y equals c to y equals d. And here we're going to set our representative rectangles horizontally. And what we would do here is integrate, find the area of one rectangle, and then sum the areas of all those rectangles over the region. So here we say our area is the integral from c to d, the integral from h1 of y to h2 of y, dx, dy. And our order of integration is the opposite. We call this type of region horizontally simple. And sometimes, depending on the region of integration or by the function that we're integrating, it's going to be beneficial to set up the integral one way or the other way. Yes?
Could you do it like on the last one where you do it horizontal and just go from A to B? Or is that...
Well, the problem with that is the upper and lower No. So it doesn't always work that way. So, and we're going to see some examples of that. So you can't, when you change the order of integration, you can't always just switch things around.
You should always go from one curve to the other.
Yes, one curve to the other curve. All right. So the key, one of the keys in chapter 14 is going to be going from the region to limits of integration. So to be able to translate from a region to the limits of integration, and also be able to translate from the limits of integration to a region. So that's going to be one of the key tools that we're going to develop in chapter 14, is the ability to go back and forth, because that's going to be important. And we'll do some examples coming up to show why that is the case. All right, so I want to go through some examples of finding areas of plane regions using iterated integrals. And again, we're not finding areas of plane regions using iterated integrals because it's easier than what we've done before, or because it's better than what we've done before. It's because it gives us a geometric interpretation of this, and it gives us practice doing this process of going from regions to the limits of integration and going from limits of integration to a region. All right, any other questions before we go on with some more examples? All right. So here's our first one. The rest of these examples are just going to be setting up and evaluating iterated integrals. So we want to find the area of the region.
Or all we have left examples.
Yes. All right, so we're going to find the area of that region. So this is our region here. I like to do this. That's our region. We want to find the area of that region using an iterated integral. So we're going to here would we set our rectangles vertically or horizontally?
Vertically.
We want to set them vertically because we want our inner integral to have our variable limits, and our outer integral to have the constant limits. So we're going to set vertical rectangles. I usually draw a little rectangle just to help me visualize. There's my little rectangle. So our area is going to be the integral, and if it helps, you can write your inner integral first. And this is going to be, I'm going to put, you don't always have to do this, but this is y equals 0 to y equals 1 over the square root of x minus 1. So on this rectangle, y is going from 0 up to the function. And we do dy. And then x is going to go from 2 to 5 dx. So we're integrating this way up to the function, and then we're adding up the areas of all those rectangles. So when we do our first integral, we get the integral from 2 to 5. The integral of dy is just y, right? So we get y evaluated from 0 to the 1 over the square root of x minus 1 dx. So this is just the integral from 2 to 5 of 1 over the square root of x minus 1 dx. Mm-hmm.
What would it look like if we don't have just dy on the first integral? Like how would that area area look like? What would that area look like?
If we had a function in here,
Yeah. What
So-
would that area look like though?
you're talking about how would we interpret that?
Yeah.
So we'll talk about that in 14.2. But what that would be is that function. If you had a function in here, you could think of that as a surface above. So z equals something, x squared plus y squared. So you'd have a paraboloid up above here, and you're finding the volume of that chunk of the paraboloid that's bounded by that region.
If we're doing areas, we're always going to have dy. If we're doing a volume, then we're going to have
Some function in there.
dy.
Yeah.
Okay.
And then we'll give other interpretations of a function inside an iterated integral, other than volumes. This is a nice, easy U sub. This evaluates to, and in chapter 14, and also in chapter 15, we're going to do this a lot. I'm not going to go through in detail the evaluation of the integral. I'll say this integral evaluates to such and such. If you're not sure, you should go and verify that on your own. So that gives us 2. That's a nice, easy U sub. All right, questions there?
Is there an advantage to iterated integrals later? Because now wouldn't it just be easier to do the regular integral?
Yes, so we're not doing these because there's an advantage. We're doing these to be able to translate, to give a geometric interpretation, and to work on setting up our limits of integration.
Oh, will there be an advantage?
Yes, because we're not going to just be finding areas using iterated integrals. We're going to do other things with iterated integrals.
So this is just kind of like,
This
we already
is
know how to do this.
right. This is working on setting them up. All right. Did I already set up a page? No. So here, this is our region. All right, is calculus even an advantage at all here? No. Geometry, right? This is just a quarter of a circle. Well, let's set up an iterated integral just to set up our limits of integration. Would we do vertical or horizontal rectangles? We could do either vertical or horizontal. Just so that you know, my preference when I set them up, I tend to always, when I can, set up with vertical rectangles. I just visualize them that way. So I would use in this case, I would use vertical rectangles. So our area is going to be the integral from 0 to 2. X is going to go from 0 to 2. Y is going to go from 0 to
Plus or minus the square root of
it'd just be plus, right? Because we're just going up.
x squared plus
4 minus x squared.
4.
We have to solve for y here. Y equals the square root of 4 minus x squared. And my order would be dy dx. Well, after our first integral, we get the integral from 0 to 2 of the square root of 4 minus x squared dx. And that's a trig sum.
Which just,
And what do we end up with here?
6 according to Sean.
it should be,
Pi.
Yeah, 4 pi divided by 4,
4.
so it's just.
pi.
Pretty close. Yeah. Our one's 4.
And what we're going to do eventually is, well, this is a quarter of a circle. Wouldn't polar coordinates make more sense?
Sean said it. I don't know about it.
So we're going to translate iterated integrals into polar coordinates as well. And that's going to be helpful if we have a function in here when we're not just finding an area, we're finding a volume, or we're finding something else to translate into polar coordinates. When we do 3 iterated integrals, when we talk about triple integration, we're going to evaluate those in cylindrical and spherical coordinates. All right, let's look at another one. And that is our region. And we want to find the area. So are we going to want vertical or horizontal rectangles here? I would say vertical. We could use horizontal rectangles, but if we used horizontal rectangles, we would have one set of limits of integration here and another set here. So we'd have to set up 2 iterated integrals. So I would say if we do vertical rectangles, I'm going to do those in that one in blue. We just have to set up 1 iterated integral because our upper and lower limits of integration stay the same between the same 2 functions for the entire region. So I'm going to say vertical rectangles. So our area is going to be the integral. Y is going to go from x to 2x. And x is going to go from 0 to 2. And we evaluate that integral. This turns into nice easy u sub, and we get 2. The area of that region is 2 units.
Could we also have just used geometry for this?
Hmm?
Why would
Yeah.
you
U is x. That's just a direct integral, right?
Yeah, you did the same.
you don't even just do it, it's just done.
All right, so with iterated integrals, we can always use either order. So the example when Ben asked, well, could we do horizontal rectangles on that vertically simple region? You could, but you would have to find the different limits of integration for different horizontal rectangles. You will get the same answer either way. One order is usually going to be easier, and also depending on the integrand, one order is going to be able to be evaluated versus a different order.
Could we
Yes.
use this to find something that, like in the past, we had to have one side be a flat edge? Could we use this method to have something so a square with all curvy sides? Like.
All right, so that's a very good question. So in first semester, we talked about planar lamina, and we talked about moments and centroids, and we had to use a lot of simplifying assumptions about where the center of mass is, that kind of thing. With iterated integrals, we don't have to make those assumptions. So we can find the centroids of, we can also find centroids of regions with variable mass.
But we could use this to draw any shape
Mhm.
and,
Any shape, right.
and set up some sort of a rectangle situation.
Yes. All right. So for this one, we want to sketch the region. and then switch
Oh, difference.
the order of integration.
Oh, right.
So we want to change our order of integration. So here's our integral, 0 to 1, minus square root of 1 minus x squared to square root of 1 minus x squared dx. Sorry, this should be y's, sorry. Dx dy.
Is that 1 plus y squared on that?
1 minus. All right, so from the limits, limits tell us that minus square root of 1 minus y squared is less than or equal to x, less than or equal to square root of 1 minus y squared, and 0 less than or equal to y, less than or equal to 1. So what is that region?
Well, we have some lines.
It's a circle.
What is x equals square root of 1 minus y squared? A circle. And what is this minus and plus here?
Plus or minus, so it's the other way around.
Does it go, well, x is going from here to here. It's a half circle. Whoops. There we go. This is x equals the square root of 1 minus y squared. And here, this is x equals minus the square root of 1 minus y squared. And the order of integration tells us that originally our rectangles are horizontal. X is going from this curve, the negative part of the curve, to the positive part of the curve. And y is going from 0 to 1. And x, those points of intersection would be negative 1 to 1. So we switch the order. X goes from negative 1 to 1. Y goes from 0 to the square root of 1 minus x squared dy dx. Notice we just didn't turn things around. We had to rewrite our limits of integration. They don't just switch when you switch the order. So for the vertical rectangles, this would be our area of that region. And we could evaluate both integrals and come up with the same thing. Questions there? All right, let's look at another one. Again, we're going to sketch the region and change the order of integration.
How many samples do we left? Whoa.
One more after this. That's a 9. All right, let's sketch this region. First off, are these rectangles vertical or horizontal? Vertical. So we're integrating with respect to y first. So y is going from square root of x to 3. Well, there's y equals square root of x. And there is y equals 3. So my region is here. And my rectangles are here. Y is going from the square root of x to 3. And x is going from 0 to 9. So we want to change the order of integration. So we're going to put our rectangles horizontally. So our inner integral is going to be x equals 0 to x equals 0 to this function, y squared. This is x equals y squared. And that's going to be dy. The outer integral is going to be 0 to 3. So that would be that integral with the order switched. We would get the same answer, either one we evaluated. But notice that we just didn't switch things around. We just didn't turn things around. We had to re-find our limits of integration. All right, questions there? All right, last example. All right, so we're given this integral. We might not know it now, but if you went to try to evaluate the integral of e to the minus y squared dy, you would have a lot of trouble. It turns out that the integral of e to the minus y squared dy is not integrable in terms of elementary functions. You can't do it. Well, it's impossible to do that integral.
So we just don't do it, like, right?
Whoa, I've never seen it.
Yeah, this is an impossible integral. Switch the order. So let's sketch the region. This tells us y goes from x to 2. And x goes from 0 to 2. So let's switch the order. So we get the integral, our integral dx is going to go from what to what? We want to do this way, 0 to y. And y is going to go from 0 to 2. Well, look what happens now. What's that integral? E to the minus y squared dx. X, e to the minus y squared is constant. So that's going to be the integral from 0 to 2 of x e to the minus y squared, evaluated on 0 to y, dy. And that gives us the integral from 0 to 2 of y e to the minus y squared dy. And what is that? That's a u sub. So we transformed that integral into something that was impossible to something that's easy. And this comes out to 1/2 1 minus e to the minus 4 when we evaluate that.
Hang on, I don't understand why that was so hard. It's just a triangle. Why is that so hard?
This integral, it's not the region. This integral is, you can't evaluate that integral.
Try it.
It's just like a hole in mathematics.
Yep.
That's just bad.
So if you wanted to try to evaluate that, you'd have to write a Taylor series or do an approximation.
Why is it like that? Why is that one just...
Yeah, it's the same with cosine x squared. You can't evaluate the integral of cosine x squared.
Oh, no, you can. It's turned into a...
just made an approximation. If you make the approximation to turn into a Taylor series, you take the integral of the Taylor series. Well, it does work.
No, yeah, physics is one of them.
All right, so all of these problems are setting up
Wait, so
iterated integrals, changing the order of iterated integrals, evaluating.
If you put e to the negative y squared into your calculator to try to do a definite integral, will it like do a Taylor series and try to figure it out, or will it just say error?
That's how it always
Yeah, it just your calculator always does it numerically.
So could your calculator do that for you?
Well, yeah, but it's an approximation.
But a TI-89 would not give you
It would do it numerically.
right. It would do it numerically.
I actually tried it. It
Right.
just spit back the same thing.
Right.
Thanks for that. I typed it in and I hit enter and
Yeah.
it gave me what I typed.
So yeah, the integral equals the integral. Yeah.
so wait.